Hello, my name is Andrew Gilbert and I'm here to present my work on semantic estimation of 3D body shape and pose using minimal cameras. We present a method for video-based performance capture that is able to estimate both 3D skeletal pose and shape, i.e. volume or occupancy, of a subject accurately from multi-viewpoint video, but using as few as 2 camera views. Uniquely, we do this without a parametric shape model, i.e. a simple model, or without the need for worn markers or sensors, nor a large camera count. Our technical contribution is the ability to learn a generative model that accepts a coarse, poor quality volumetric proxy formed from a low number of wide baseline camera views of a subject. And in a single inference step, we estimate both the skeletal joint positions, i.e. the pose, and refine a higher fidelity volumetric reconstruction from the rough proxy, i.e. the occupancy. Our work is inspired by contemporary super-resolution algorithms that apply learned priors to enhance visual detail in images, to instead denoise low-fidelity geometric proxy volumetric data into high-fidelity proxies and estimate 3D pose. We use a multi-channel symmetric 3D convolutional generative encoder-decoder with a dual loss to enforce the learning of a latent embedding that enables inference of the skeletal joint positions and a volumetric reconstruction of the performance, which is all constrained by a discriminator. To estimate the pose and proxy, we propose to lift 2D visual features to form a 3D voxel features from the 2 distinct modes created by the RGB images of each camera view, a 2D foreground occupancy map and 2D semantic joint detections. The probabilistic occupancy provides a low fidelity shape-based feature relatively invariant to appearance and clothing that complements the semantic contextual 2D joint estimate that provides an internal feature description. We use a multi-channel based probabilistic visual whole, or PVH, where we decimate the capture volume into 5mm cubes and each as voxels, and each voxel is assigned a probability of occupancy and semantic joint occurrence. There will, however, be phantom limbs and blocky false positives due to the number of cameras used, which is generally just 2. Training minimizes the error of the encoder and decoder outputs. The encoder yields a latent feature representation via a series of 3D convolutions. Each convolutional layer is followed by a batch normalization and ReLU in the generator and convolutional slides for a layer in both the encoder and decoder. The loss function is the weighted sum of the MSE of the 2 network outputs. The encoder-decoder network described in the section above with the dual volume and joint pose loss can produce consistent results. However, we employ a generative adversarial network. Again, the encoder decoder model we refer as a generator estimates the improved volume, while a discriminator maximizes the chance of recognizing real PVH volumes as real and generated PVH volumes as fake. Deeper networks and image restoration tasks can result in finer image details being lost given the compact latent space. The recovery of this detail is an undetermined problem exacerbated by the need to reconstruct the additional dimension in the volumetric data. We therefore add skip connections between the convolutional and deconvolutional layers. If we were to omit these skip connections, the details of extremities such as lower arm positions is poorly estimated by both the volume and 3D joints. We also enforce temporal consistency through 2 LSTM layers. These help to smooth noisy individual joint detections to enable a smoother prediction of the joint estimation. To justify the performance of our proposed approach, we report mean per joint position error, the mean 3D Euclidean distance between the ground truth and estimated joint positions of the 26 joints. We performed quantitative evaluation on the 3 datasets, total capture outdoor, and human 3.6. Here, this shows the results of two unseen sequences on the total capture dataset with the pose and volumetric reconstruction. This table quantifies the pose estimation error between previous approaches using the general multiple camera views or additional data modalities and our proposed approach with only 2 camera views. We outperform the best camera approach by 8mm, indicating the importance of the GAN loss and semantic 2D joint estimates. Before refinement, the ablated view PVHs at the bottom demonstrate phantom extremities and lack fine-grained detail. These crude volumes will be unsuitable for pose estimation or reconstruction. However, our approach can estimate the joint positions accurately and also clean up and hallucinate a volume equivalent to one produced by the unabated 8 camera viewpoints. To understand the influence of the individual components and design decisions, we perform an ablative analysis of the tracking accuracy for our individual contributions as shown in this table. Each part of the process enables an improvement in the accuracy performance, especially the use of the temporal information and the dual loss in the approach, providing an error of 35mm. The inclusion of the 2D joint estimates into the dual channel PVH further reduces this by 4mm. The inclusion of the discriminator to enforce improved 3D occupancy enables the loss to be further reduced to 21mm per joint using all 8 camera views. The greater the number of cameras, the more visually realistic the PVH is. However, it is possible to remove a large number of these cameras with little or no impact on performance. To demonstrate the approach on the envisaged scenario on a less constrained capture environment, the framework was tested on an internally produced and more challenging dataset, Total Capture Outdoor, a multi-view video dataset shot outdoors with moving and varying background of trees and illumination. We used 4 of the 6 camera views placed in a 120-degree arrangement around the subject with a large 10x10 capture volume. The subject can be far from the camera and small in the scene, making traditional 3D pose estimation and volume reconstruction very challenging. The video illustrates that, despite the small scale of the subject in the camera images, a plausible estimate of both the pose and occupancy can be recovered from a coarse input. Perform a further quantitative and qualitative evaluation on the popular Human 3.6M dataset as shown below. Each video is captured using 4 calibrated cameras arranged in a 360-degree arrangement, and we follow the standard train and evaluation protocols of the dataset. As you can see from the 4-cam input and 3D pose, it is very poor. However, we are able to clean up the reconstruction and the 3D pose to provide excellent results. Given the quality of the approach, it is possible to estimate a wide variety of human motion from only 2 camera views with high accuracy with no drift or jitter. From sitting, crawling and detailed actions with the hands and legs, we present in the table on the right 3 variants for the Human 3.6M dataset. Human 3.6 model, which is the baseline approach using the specified Human 3.6M training data with the 4 cameras, assuming that the semantic 2D joints will compensate in part for the phantom parts and ghosting that occurs in the occupancy voxels. Then we have TC model, where we transfer a pre-trained model from the total capture dataset without any further training to estimate the pose and reconstruction as if 8 cameras were used at acquisition. Then finally we have TC plus fine-tune, where we do 2 epochs of fine-tuning in addition to using the pre-trained TC model on the Human 3.6M dataset. As you can see, our pre-trained plus fine-tuned model dramatically improves on other prior works. This proposed work generates 3D joint and 3D volume proxy reconstructions using only a minimal camera set of 2 wide baseline cameras, through learning constrained by dual loss on the joints and a generative adversarial loss on the 3D volume. The dual loss in conjunction with the discriminator in the GAN framework delivers state-of-the-art performance. Furthermore, we have demonstrated that a trained model with plentiful data from the total capture dataset can be used to improve performance on other datasets, in this case human 3.6M, that have a limited number of camera views. Thank you for watching.